Let's dive into the mean value theorem. It easily could have been called the nice value theorem, but the word mean here stands for the word average. So it easily could have stood for nice value theorem, where the nice value simply means average value. Our objective today is to actually understand Rolle's theorem and how it applies to certain functions and how it actually relates to the mean value theorem. We want to understand the mean value theorem and apply it to functions. And it's important to understand that there are three very important consequences of the mean value theorem. Here's a hypothetical situation that you may have ran into, or maybe a friend has ran into a situation like this, but hopefully you'll never be caught by the police. Suppose a state patrol officer saw a car start from rest at a highway on-ramp. The officer recorded the car and radioed ahead to another patrol officer 30 miles along the highway. When the car reached the location of the second officer, 19 minutes later, the car was clocked 65 miles per hour. The driver of the car was given a ticket for exceeding the 70 mile per hour speed limit. Why can the officer conclude that the driver exceeded the speed limit? Now you might be able to reason this out through, your algebra experience. But what you probably don't realize is that you had to assume some calculus scenarios, specifically the first derivative. We'll later on support the officer in writing the speed ticket in greater detail. But before we can do that, we actually need to introduce a couple of theorems. The first one is being Rolle's theorem. Rolle's theorem goes something like this. If f is a function such that f is continuous on the closed interval ab, and f is differentiable on an open interval ab, and the function values at the endpoints are equal, then there is a critical number in open interval ab such that the derivative evaluated at this critical number is equal to 0. Now the proof is rather simple, but I will add a few pictures here. So the proof consists of 3 cases, but they're all related to algebra and how you draw functions. So let's draw some models here. Case 1. What if your model is a constant function? So there is a k value here and your model is actually a constant. So there's f of x is equal to k. Now look at the slope of the tangent line at any point and notice there's a slope there, and so there's an corresponding x value down here. So there's actually a lot of these. Here's a first one, there's a second one, maybe the third one's over here. But in this situation, I mean, if you're going to take a closed interval a to b, notice that all your x values here are going to be called critical numbers. So there you go. We know that a constant function is differentiable, and so when you differentiate a constant function, you're going to get 0 for all x. So all these x's are actually critical numbers of the function. And we can see that the slope of the tangent line is actually 0. And there's lots of tangent lines here, but they're actually all the same tangent lines. Let's move on to case 2. Case 2. What would the function look like now? It says, suppose on this closed interval, a to b, there's an x value such that f of x is greater than f of a. So let's put the x value somewhere here. We know it's greater than f of a. So this is a hypothetical picture. I just got to make sure f of x is greater than f of a. And if I play connect the dots here, and we know that the function values at the endpoints are the same, then we're going to see something like this. We'll see some function like that on a closed interval a to b. Then f must attain its absolute max. And notice this x value gets renamed to be c because it becomes a critical number. Since f is differentiable and f has a local max at c, the derivative evaluated at c is in fact equal to 0. And you can see that at the picture here. Okay, so in this case, x does become c. And this particular picture is going to play a very important role in the upcoming mean value theorem. So make note of this picture. This is a really good picture. Now let's look at case 3. How would you draw this function? Start with the closed interval again. A, B. Now what if there's an x value that is lower than f of a? Let's say f of a is over here, and let's say the x value is right about there. And that function value is now lower than f of a. It could be really low. It could actually be in the fourth quadrant. But you know the endpoints yield the same output values. And so when you draw this function now, when you play connect the dots, and you know that this function is going to be differentiable, it's going to be smooth, it's not going to have any corners, there's no gaping holes, we could see the slope of the tangent line here. You know, maybe I need to round this a little bit better. There. You can see that the slope of the tangent line here, f prime evaluated at x, is going to be 0. So that means x here is a critical number. We can simply call x equals c, so that the letter c stands for a critical number. And that will conclude the proof of the third case. In this case, you won't have a local max, but instead you will have a local min, because all the output values are actually a little bit higher than this minimum here. Now that's Rolle's theorem, where the output values are actually equal, the function is continuous on a closed interval, and differentiable. Now the mean value theorem is very similar. However, the endpoints do not have to be equal. Okay, the function value at the endpoints do not have to be equal, so that means your pictures are a little bit slanted. So if they're not equal, you can see there f of a and f of b are not equal. You're going to see a little bit of a tilt in your picture. Clearly not equal to f of b in this picture. So that's the major difference between Rolle's theorem and the mean value theorem. Now with this tilt, the conclusion is something more powerful. It says if f is differentiable on this open interval ab, then there is a critical number c in ab such that when you evaluate the first derivative at this critical number, instead of it being 0, it's going to actually equal the average value. So just remember that the difference between Rolle's theorem and the mean value theorem is Rolle's theorem says the derivative being evaluated got you 0. Now you got to remember that this gives you the average value. Okay, that is the average rate of change. And so at a certain critical number, instead of getting 0, we're going to get an average value or an average rate of change. Now the proof of the mean value theorem is rather astonishing because it actually just uses Rolle's theorem. So the key here is actually define a new function. And I'm going to point it out. I'm going to define this new function here, h of x. H of x is going to be the difference between f of x and the equation of this secant line. So if you think about it, because the endpoints are not equal, or the function values at the endpoints are not equal, what we're going to do is create this function h of x so that you get a mathematical hammer. And let me try to illustrate this with a drawing here. It's kind of like you take a hammer here and you pound this endpoint down. And you pound it down so that it actually lines up. And so when you draw h of x will look like a similar case that we saw in Rolle's theorem. So this becomes h of x after hammering that function and defining it with algebra. You end up getting something like that. Notice now the function h of x will have output values at the endpoints. And what are those endpoints? I got to remind you, it's a to b. And so down here, it's going to be a to b. And so with careful algebra here, we're going to define h of x to be the difference of the function value and the function of this secant line. And then you get something like this, and we're going to be able to apply Rolle's theorem. So the proof of the mean value theorem is dependent on Rolle's theorem. Once you define that function, h of x, there it is, define it with algebra. It was the higher function minus the function which resembles the secant line. Okay, once you do that, now h of x is the difference between two continuous functions, so it's actually continuous on the closed interval a to b. H is also differentiable on the open interval a to b because these functions here are differentiable on the open interval from a to b. Evaluate at a, you get 0. Evaluate at b, you get 0. Now, we concluded all the requirements of Rolle's theorem, so we're going to go ahead and conclude with Rolle's theorem that there is a critical number in the open interval AB such that the derivative of h of x evaluated at c is going to get you 0. And when you substitute everything, you substitute the derivative of h evaluated at c, which is this. Now you're just going to add this quantity to both sides. And notice you get the mean value instead. Okay, so the derivative evaluated at c is actually going to be the mean value.